Okay, I'm going to be talking about a project that's looking at the next generation post SLSTR called the ASLSTR. And here's the project team. It's led by Paolo Cellini from ESA, and the PI Institute is University of Reading, who will be concentrating on the uncertainty analysis side and SST analyses, led by myself with Chris Owen and Claire. And the level 1 uncertainties are being looked at by Raoul and Dave Smith, and the LST analysis from University of Leicester and APMA with Darren and Vitamin Sophia. Aerosol optical depth, University of Swansea, Peter North and Kevin, and fire will be looked at by Martin Rooster. So the idea of the project is to look at different design specifications as well as channel selection. Here I list the channel selection. In white are the current SLSTR ones, in yellows are the new proposed ones, and one of our tasks is to decide which of the new ones, if any, would be useful. I would also say you can note that the spatial resolutions increased from SLSTR at 1 kilometer down to 500 meters. So in terms of the task we've been asked to look at, task 1, which is led by me, which is essentially analysis of the SST uncertainty budget from level 0 through level 1 into SST, including possible architectural changes, such as currently we have 2 black bodies, conical scan, maybe 1 black body in space would give a different solution which might work. And also the idea is to use the metrological approach to the uncertainties. Second task, which I won't be saying very much about in this presentation, is to look at all the different channels for ASLSTR and look at them in terms of application use and recommendation. Task 3, led by Leicester, is to do with the optimization of spectral channels such as central wavelength, bandwidth, etc., plus estimates of signal to noise, goal threshold values for different applications. And then task 4 is looking at the synergies between ULCI and SLSTR. So in terms of level 1, we're doing things like create uncertainty trees. This is an uncertainty tree for SLSTR, which Dave produced. On the outside, for those of you who don't know, are all the possible sources of error that feed into the obtaining of, in this case, irradiance, and it traces how those errors get propagated through all the different processes to end up giving you a final uncertainty budget. And this is a fiduciary-like approach. So Dave has done this for the main drivers of error, including this possible architectural change. So you've got two black body case, which is current SLSTR, and you've got 1 black body and space view. So for the 2 black bodies, you end up with actually having the black line showing that you're beating the goal uncertainty, which is good in the SST regime at least. For the 1 black body, you can see that you're not meeting the goal for SST, but you are getting lower uncertainties at the very cold end, which some applications would find useful. But in terms of SST, I don't think there's any reason to change from the current 2 black body configuration. And then in terms of the SST uncertainties themselves, in terms of looking at it just in terms of the retrieval uncertainties, we've basically taken the 2100 profiles that we used to define the retrieval coefficients in CCI and C3S, etc., which uses LV-LRTM spectra based on 2100 atmospheric profiles and SSTs and total column water vapor, etc. ranges. And you basically get the brightness temperatures, create retrieval coefficients, and then use those retrieval coefficients on the brightness temperatures to see how different you are from the input SST, and that gives you an estimate of SST error. And here are the distributions of those errors with the standard deviation or uncertainty shown in the boxes. So we've got N2, the standard ones on the left, and on the right, there's also, say, an N2 with an addition of an 8.7 micron channel or an addition of 8.7 and 4.05 micron channel. And what that actually shows is the addition of the 8.7 micron channel, as you would expect, does actually reduce the SST uncertainty, particularly for the N2 and D2 retrievals. And we're also going a bit further than that by trying to do orbital simulations of SLSTR based on SLSTR for a calendar year, a day a week, in part to look at trend uncertainties, but also error correlations and the actual impact of aerosol on the data, because even though the current operational coefficients are aerosol robust and have aerosol corrections in, This is using CAMS aerosol in the simulator to try to see what's the uncertainty on top of that. But we've done the simulations, we haven't done the analysis yet. In terms of LST, which of course is equally important, they have really concentrated their analysis to date on the 8.7 micron channel because, as you can see here, it enables you to get a better handle on the emissivity, which is extremely important for LST. And they're beginning to look into constraining the central wavelength, but they think the width is most likely to be constrained by required NE delta T. But again, the 8.7 micron channel will be a strong addition to the channel set and is likely to be recommended. In terms of SST optimal channels, we looked at shifting real spectral response functions, such as taken from Sentinel 3A, 7S, 809, added in the MODIS 4.05 and the Siberi 8.7, shifting each channel at a time, looking at how the SST uncertainty varies. You can see that there are times when there are minima in the SST uncertainty at sort of shifted wavelengths. So this sort of analysis is helping to begin to map out maybe sort of an optimal central thing, but it is true to say that the 8.7 improves things, adding the 4.5 doesn't. But beyond that, using real spectral functions, you can't study how the full width half maximum needs to change. So we've also added in a flat top spectral response function where you can vary the full width half maximum and the central wavelength and how flat it is at the top. And we've just started doing this, so gridding on those three parameters, seeing where the minimum SST uncertainty is for different retrievals. And you actually see it looks a bit complicated, especially the S9. And I think this is more related to the optimization surface, if you like. You're probably getting local minima. Maybe the grid isn't being well enough to find. And this currently is only done, again, for you worry about one channel, fix the other three, or etc., and see how the statistics goes. We really need to do it by varying all channels simultaneously. So we started looking into an optimization process for this as well. Fire, of course, is also a very important product or application. Martin Wooster's been looking at this, and he's basically been looking at what happens with the spatial resolution. It goes down to 500 meters, and you can see, the maximum power is about 1,000 megawatts. And in fact, if you look at most fires, which don't get up to that extreme, and you take that the 99.5%, it's more like 250 megawatts, which if you take into account atmospheric corrections, etc., you end up finding out that you want the 11 micron channel S8 to saturate above 340 Kelvin. And if that is true, you don't need the extra F2 channel. And in fact, this 340 Kelvin is also at the maximum brightness temperature needed for LST. So I think one requirement would be the saturation point. And then in terms of AOD, again, studies have begun, although there aren't results at the same level that I can show, unfortunately. But one thing that has come out already is there is a recommendation from the aerosol people to flip the oblique view back to forward view, because you get a better coverage globally in terms of aerosol if you do that. And then there's synergy. So there's a work plan, you're folding in all the Copernicus services going into synergy products, but we're also working with the AOLCI team to look into the co-registration question, and they've done quite a lot of work on that. So we're also looking at that. And so to end with, we're looking at next generation, looked at possible design changes, although I don't actually think there's any strong evidence for a change for two black bodies at the moment. Looking at adding in extra channels, maybe two. My guess is it's probably going to be the 0.44 and 8.7 if there's only two allowed. We're providing metrologically traced uncertainties from level 1 to SST. We're setting up the code as we speak using MPL tools, but also adding in sort of aerosol uncertainties and also correlation trend analysis and error correlation. Channel specifications, we're trying to find optimal values, which is underway for SST, LST, and aerosol optical depth. And FAR has already told us something about saturation levels. And then there's the synergy work. So most of the analysis code has been set up. We're working towards optimal solutions now, and for the definition requirement specifications, and we have 6 months left to go. Thank you.